going to do this. So I have a linear space. Suppose that X is a finite spanning set. So I'm going to let X be x1 up to xn, and I'm going to let Y be y1 up to ym. So in this language, right, so X is a spanning set, Y is a linearly independent set, I need to show that m is less than or equal to n. This should say fewer than or equal to. That's a typo, and it will be corrected by the time you see it. So I'm going to show that there are more than or equal to the number of sets elements of X than Y. The way I'm going to do this is I'm going to consider, I'm going to set a set Z. How about Z naught? I'm going to set equal to X. Z1, I'm going to set equal to X union Y1. Now, what do I know about this? So this is equal to, right, X1, Xn, comma Y1. This is going to be a linearly dependent set. How do I know that? I know that because X spans. So there's a C1, X1, plus C1, Xn, that's equal to Y1, because that's what it means to be a spanning set. So what I can do is I can use a previous theorem, and that is theorem 94 here, is that if you have something is a linear combination of a bunch of these V's, you can replace one of those non-zero things. So you have to have a non-zero coefficient in order to do that. Replace one of them with the thing on the other side of the equal sign. So what does that mean here? That means that I can replace one of these x's equals z1 minus some xi union y1, where ci can't equal to 0, because that allows me to use that allows me to use theorem 93. By theorem 93, Z2 still spans V. And this is basically the game that we're going to play. We're going to keep on doing this until we reach, how about ZL, which is going to equal ZL minus 1 minus some xi, maybe I'll call it xj because it might be, this is probably different because it's gone, union y sub, what's going to be? L minus 1. And so I can continually do this. And the key thing is, so if I have this ZL, I'm going to continue along this lines, I can make ZL plus 1 to be ZL minus some x sub k. I'm going to explain this all in just a second. It should be a little... I'm going to explain how I get this one from the previous one. And so in other words, once you have Z1, you can get Z2. Once you have Z2, you can get Z3, etc. Because here I have some mixes of x's and some mixes of y's in the CL. Because what I'm doing is I'm taking out an x and I'm replacing it with a y. Take out an x, replace it with a y. So what I have is I have some maybe D1. I'm just what's the best notation for this? D1 x plus D2 x sub, I don't know what subscripts are left there, plus da 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 plus D, running out of letters. D, I call it U, and some x, plus, now I have a bunch of y's, about E1, y. I don't know which y1. I know that the y1 is in there, and then y2, then y3, etc. Plus e2, y2, plus da da da, plus el minus 1, yl minus 1 is equal to yl. Because at each stage, I'm going to show that you have something that spans the entire thing. So if I have this set, then I know that I'm going to assume that I have a spanning set here. I can get to the next set. And why is that a reasonable assumption? If I have a spanning set and get to the next one? Because I know that this one actually is a spanning set for 2. So that'll allow me 2 to get to 3. And then if I know that 3 is a spanning set, which is essentially what I'm doing here, then 3 will get you 4, etc., etc. So as long as I have some coefficient here that's non-zero, I can replace it with y sub l. But I only want to replace these. Now, so I want to make sure that the non-zero coefficient isn't one of these e1s. But on the other hand, I'm not so concerned because what do I know? I know that, here's the thing that we're actually proving. I know that y is linearly independent. So it cannot be that all of these things are 0. It's impossible to have 0x plus da 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 plus 0x plus e1 y3 plus el minus 1 yl minus 1 equal to yl. It's impossible for all of these to be 0. The reason why is because this is linearly independent, since y is linearly independent. So since the y's are linearly independent, that means that there is no such coefficients that you can put together that equal another one, unless they're all equal to 0. Because you can imagine just bringing this one over to have negative yl, and then throwing all the rest of the y's with just 0 coefficients. You'd have e1 plus da 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 plus el minus 1 minus yl plus 0 yl plus 1, etc., etc. And that would give you something equaling 0, but the coefficients would not all be 0. So that's impossible. So I know that some of these d's have to be non-zero. Well, I'm just going to pick one of these d's to be non-zero, and then I can replace that, call it x sub k, and I'm going to replace that with this y sub l by 94. Here. So I can replace y sub l is equal to a whole bunch of stuff, and so I can replace it with that. And this should be 94. So what I've proved is that I can get, as long as this thing is a spanning set, then this will also be a spanning set. By theorem 94. So in other words, Z1 I can get pretty easily. Z2, these aren't the best names, by the way. This should probably be Z naught or something like that. Z2 is a spanning set by 94. We're certain of that. But once I have this as a spanning set, I can repeat the process again and again and again, and I keep getting spanning sets. But at some point, I'm going to run out of these y's, because I keep having these y's in here. Since ZV is always a spanning set, we can do this. In other words, basically every time we get a new z, what happens is we replace one of these x's with a y. Do this indefinitely. But that's not true. We can't do it indefinitely until we run out of y's. And that's sufficient. Because if I can keep on doing this process indefinitely, well, not indefinitely, because I'm going to run out of y's to replace with at some point. But what happens here? If I replace it, if I have a y, what happens in each step is I replace an x with a y. If for every y I can replace it with an x, that tells me that there are at least as many x's as y's. It might be that there's exactly as many, which is why this is not an accurate the same. It should be fewer than or less than, or fewer than or equal to. So what I'm doing here is again, here's the broad strokes. I'm going to take my spanning set. I'm going to replace one of these, I'm not sure whichever one has a non-zero coefficient over here, with y1. By theorem 94, that's also going to be a spanning set. Now I can play the same game again with a new spanning set, z2, and the y's where it's y2 up to ym. Well, that's going to be, I can do that, I can replace an x with that by theorem 94 because I know that there's going to be a non-zero coefficient among the x's. Why do I know that? I know that if there were only non-zero coefficients among the e's, that would mean that I would have a situation where you can take a linear combination of the y's equal to another y, and that is something that happens when they're linearly dependent, but y is a linearly independent set. So I can keep on doing this process, each time replacing one x with one y, and I can keep on doing that till I run out of y's. If I can keep on doing that till I run out of y's, that means I haven't run out of x's, which means that there are at least as many x's as y's, which means that there are fewer than or equal to the number of elements in y as there are in x.